Hello, algebra students. We're going to talk about transformations. The first kind of transformation we're going to talk about are translations. So that's the packet you should have out now. A transformation is a change made to the location or the size of a figure. The new figure that results from one or a combination of transformation is called the image. So we can talk about the original, that's the original picture, and then the new figure is the image. The vertex or the corners of the original figures use a plain capital letter, whereas the image, so the one that has been translated, of like point P would have the notation P with an apostrophe. So I'm just going to show that a little bit bigger. So we would show whatever point is then translated, we would use the same capital letter as the original, but we add a little apostrophe to show that it's the image. If we would make a second image from the first image, so now we have a third shape, we would label it with 2 apostrophes, and if we translate it again, 3, etc. So as the packet indicates, the first kind of transformation is a translation, which in lower levels of math you would have referred to as a slide. A translation is a slide of a figure at a fixed distance. The translation does not change the original figure's shape or size. So this means translations create congruent figures. The shape will look the same, it's going to be the same shape and size, but it will be in a different location. So in order to do a translation of a figure, we need to first have a figure. So in example 1, we want to explore translations. We need to do step 1 to plot and label the points. So I'd like you to plot and label point A, B, and C on your coordinate plane, and then we'll continue. So hopefully when you plotted your ordered pairs, you got the same triangle that I did. Notice that I have connected the dots to make the triangle, and that I have labeled each vertex or each corner with the capital letter. Then we're told to follow step 2. We're going to slide each vertex 7 units to the left. To do that, I'm going to look at each vertex and just count 7 units to the left. And so that tells me where to put the image of A. So I label that with a capital A with an apostrophe to show that it's the image of A. Then for B, again, I'm going to count 7 units to the left. And put the point for the image of point B. Capital letter, B with the apostrophe to show that that's the image of B. And I'm going to count 7 units to the left for C. Capital letter C with an apostrophe to show that it's the image. I'm going to connect the dots to make the triangle. And hopefully you see that you've created the same shape and size triangle, but it is just translated 7 units to the left. When we need to decide on the ordered pairs that make up the image of triangle ABC, and so we want to record those ordered pairs. Go ahead and record the ordered pairs, and then we'll continue. Hopefully you've recorded the same ordered pairs. For the image of A, you should get -4, 2. For the image of B, you should get -4, 5. And for C, we get 0, 2. Another skill we want to work on is writing an algebraic rule for translations. So we show the original just X and Y, whatever those X and Y's happen to be. For example, point A in the original was 3, 2, but we just represent it as X, Y when we're writing the algebraic rule. Then, when we're talking about the translation, we look and try to write what the changes were. When we moved 7 units to the left, that's subtracting 7 on the x-axis, because the x-axis is our left and right axis. Notice that because the triangle didn't move up or down, there was no change to the y. And so the y in the new ordered pair, or the rule, stays just as y. For this next part, we're going to take a look at finding the length of side BC and the perimeter of the triangle. So we need to refer to our triangles, so I'm just going to move that part up on my page because I have the convenience on the video of doing that, so I can look at the triangles closely. So the length of BC is something we want to determine. Now what we're looking at here is BC, and BC is finding the length of BC, and that is in the original. I know we're looking for it in the original because of the capital letters without the apostrophe. Now granted, because we did a translation which doesn't change the shape, the length of the image of BC would also be the same. So how would we find the length of side BC? Make a choice and let me know, and then we'll continue the video. Hopefully you chose Pythagorean theorem. Triangle ABC is a right triangle. So we want to write down the formula for Pythagorean theorem. A squared plus B squared equals C squared. Now this A, B, and C refers to the sides of the right triangle, not to the capital A, B, and C in our original and our image. So the length of A would be the length of one of the sides. So I'm just going to go with the shortest side, and that side has a length of 3 units. B would be the other side of the right angle, and that has a length of 4 units. And we're looking for the hypotenuse, so that stays a variable. We square 3, we square 4, and of course C we don't know yet. Then we're going to add on the left-hand side of the equation. And then we take the square root of both sides to get just plain C. So BC is 5 units long. Now we need to find the perimeter of triangle ABC. To find the perimeter of a triangle, it's P is equal to A plus B plus C. You're just adding the 3 sides together. So we have side A is 3 units, side B was 4 units, and we just found that side C was 5 units. So we want to add those together. What you get is the perimeter of triangle ABC. Hopefully you got 12 units. All right, we're going to move on to the next kind of transformation, which is reflections for now. The practice you'll do in class. So let's put that packet away and get out the reflection packet, where we'll do example 1 together. So the next kind of transformation that we're going to talk about is reflections. Reflections are a flip or a mirror image. A reflection is a flip of a figure. The resulting figure is a mirror image of the original. A reflection does not change the original figure shape or size. So again, the shapes are congruent. So the shape is going to look the same size and shape. It's going to be the same size and shape. It's just going to have been flipped or look like a mirror image of the original. Now, what a shape looks like as a mirror image depends on where the mirror is. So you do want to note that we can reflect a figure over any line. The most common lines we're going to reflect over are the x and y axis. So what that means is if we're reflecting over the x-axis, then that means that the x-axis is the mirror line. If we're reflecting over the y-axis, then that means the y-axis is the mirror line. So you have to pay attention where that mirror line is, or what you are reflecting over as we do reflections. Reflections, like it was with translations, any kind of transformation, we need an image to transform. So the first thing we're going to do here is create an image for the original, for example, 1 for reflections. So step 1 to reflect over the x-axis is to get an original shape. So you're going to plot the points Q, R, S. Go ahead and plot those, check in on Edpuzzle, and then we'll continue. So we've got ourselves a little triangle QRS. Hopefully your triangle looks the same. We want to reflect over the x-axis. So that means that the x-axis is the mirror line. So when we draw the points for the image, it will look as if the original QRS is looking in the mirror of the x-axis and seeing itself on the other side. So let's draw those ordered pairs now. So hopefully you have the image of QRS where I do. And it should look like the original and the image are looking in the x-axis mirror at themselves. Now our goal is to write a rule for reflection over the x-axis. So we want to look at the ordered pairs and compare them. What happened to the original x and y in point Q when it turned into the image of Q reflected over the x-axis? What happened to the original point R when it was reflected over the x-axis? And what happened to the original point S to turn into the image of S when it was reflected over the x-axis? So when we write a rule, again, we start with the original x and y, and then we try to algebraically write what happened. Hopefully you noticed that when you're reflecting over the x-axis, nothing happened to the x values. The x values stayed the same. So reflecting over the x-axis, the x values stayed the same. But reflecting over the x-axis, the y values became their opposite. So we need to write the opposite of y. So when we reflect over the x-axis, we can find the new ordered pairs by saying that x comma y becomes x comma the opposite of y. This is a rule that we're going to use frequently, so it's one that you probably want to memorize. Now we're going to take our original and our image and find some information out about it based on what we know about shapes. So we're asked to find the area of triangle QRS. Now I know that's the original because it does not have the apostrophes. So I have to think about how I find the area of a triangle. The area formula for a triangle is area is equal to 1/2 the base times the height. So I need to look at my shape, triangle QRS, and decide what is the base and what is the height. The base is 3 units long. The height is also 3 units. The base and the height of a triangle will always meet at a right angle. So let's plug those values in. So the area is equal to 1/2 3 times 3. And so what is the area of this triangle? Hopefully you got an area of 4.5 units squared. Then we're going to find the area of the image of QRS. I know it's the image because of the apostrophes in the question. So I refer to my shape. Again, I'm finding the area of a triangle. So I still would use the area is equal to 1/2 the base times the height. On my triangle, I look to find the base and the height. The base is not the bottom of the triangle in this case. The base and the height always meet at a right angle. So again, the base is 3 and the height is 3. This makes sense because, as we said in the beginning, reflections do not change the shape or size. So the area of the image should be the same as the area of the original, 4.5 units squared. Now we're asked to find the length of QR. So if I look at my picture, I'm trying to find the length highlighted in green. That, hopefully you recognize, is the hypotenuse of a right triangle. So this time we're going to use the Pythagorean theorem. So you need to be flexible and ready to use the formulas you've used in the past when it's the right circumstance, and really be problem solving to decide what kind of problem you should be doing to find what you're trying to find. So then we're going to plug in the values for A, B, and C, hopefully recognizing that you're not really using the whole triangle that we drew as the right triangle. The triangle that is the right triangle, I'm going to highlight in purple. So we have a right triangle inside our original triangle. And that's the right triangle we would use to find the length of QR. So what are the two legs of that triangle? You should have written 2 squared plus 3 squared is equal to C squared. And then that would give us 4 plus 9 is equal to C squared. I'm going to finish my work over here. So 4 and 9 gives me 13. So 13 is equal to C squared. And to find C, I have to take the square root of 13. That gives me approximately 3.6. So C, or QR, is approximately 3.6 units long. Make sure you're bringing your questions to your algebra teacher and keep hold of the packets as we're going to do the practice in class.